In the last video, we counted how many integers there were between 414 and 881 inclusively divisible by 3 or 5. And I wanted to just show you one other thing, or one other perspective on it, just one little piece of it. So we did the whole problem, how many from 1 to 881 are divisible, and how many from 1 to 414 are divisible by 3 or 5. But we could have done it individually for 3 and 5 and 15 as follows. So let me just write it down here. The number of integers between 414 and 881 divisible by some number, let's say 3, is the floor function of 881 divided by 3, that counts all of them from 1 up to 881 divisible by 3, minus the floor function of 414 divisible by 3. Now this is really not anything surprising based on how we did the other one, but you could have done them individually for 3, then 5, and then 15 and added those numbers. This number turned out to be 293 minus 138. Is that what we had up there? I think 138. Let me just make sure. Yeah. So so what do we get there? 40, 55, 155. Yeah. So just another way to do it, another way to think about it, if that helps you. So let's do another case of inclusion-exclusion, this time with 3 sets. This is the 3-set case of inclusion-exclusion. So let me first of all draw a Venn diagram wherein I draw a blob for each of the sets, or if you prefer a circle, like so. And so I'm going to have an A, a B, and a C here. So let me label those A, B, and C, indicating the potential overlap and so forth for each of these. So what I'm going to do is start off this formula for the number of things in the combined set, where we take everything in A, B, and C, put them together in one set. The union of the 3 sets, using that set word, will be equal to, and I think I'll write it below to have enough room here, will be equal to the number of things in A plus the number of things in B plus the number of things in C. But we've got some double counts here. I understand that. But what I'm going to do is say how many times things are counted in each of the regions that I have in the diagram here. So for example, in this region right here, something where I put that little dot is in A, but not in either of the other 2 sets. So it's counted in the first thing here, but not the other 2, so it's counted 1 time. Whereas something over here is counted 1 time, something over here is counted 1 time in just that section. Now, if we go in a little deeper, something in here is counted 2 times, because it's in A and B. Something in here is counted 2 times, it's in A and C, but not in B. So that thing right there, something in there, is in A, it's counted here, and it's in C, so it's counted here, but it's not counted there. Yeah. Same with this here, it's in B and C, but not A, so it would be counted here. Whoops, not there, but in B and C, so it's counted twice. The thing in the middle is in all 3 of them, so it's counted 3 times. So we want to do the addition-subtraction thing so as to make this justify and give us 1 in each of the regions that we're counting each thing 1 time. So we're going to do the subtraction that we normally would do. So this will be minus the number of things in the intersection of A and B, minus the number of things in the intersection of A and C. Those are all double counted, right? That would be A and C, that would be this section here. Those are double counted. Minus the things in the intersection of B and C. Those are double counted there. Like so. So if I do that, I've subtracted once everything in both A and B. So that means these things are in both A and B, so that now is just counted once. These things are also in A and B, right? They're in the overlap of those 2 blobs, so this gets down to 2. Okay, now A and C, though that's I just did A and C. sorry. I just did that one. Let's do A and B now. A and B, that thing's in A and B, so that goes down to 1. These things are in A and B, so I'm subtracting that out again, so that goes down to 1. Now B and C, these things are counted twice. These things in this section are all counted here, and so if I subtract that, I move that down to 1. But this becomes 0 now in the count. You see I've knocked it down to 0 because everything in the intersection of all three is counted here, here, and here. So I've subtracted it 3 times, which is how many times it was counted, but I want to count it once, so I have to add back in the number of things in the intersection of A, B, and C. So that's how this little formula comes about. It's pretty straightforward to see. I've kind of made it a little ugly in that blob there, but it started out being counted 3 times, and in the end it got counted just 0 because I removed it 3 times, so I had to add it back in. Yeah, so there's the formula right there. This whole thing right here is the formula for 3 sets. Okay, add them in individually, the number of things sets individually, subtract out the number in each intersection, add back in the number of things in the intersection of all 3. So there we go. And that pattern actually continues as we go to more and more sets, but that's what we'll have for this one right here. So I want to do a problem with this just to show you in a kind of a simple way how you can manipulate with 3 sets. I am sure some of you have done this before. I think it's just as likely that some of you have not. But I'm going to save this example for the next little video.